Welcome to the talk Even Faster Exact K-Means Clustering at the 18th Intelligent Data Analysis Symposium, or IDA 2020. My name is Christian Borgelt, and I'm a professor for data science at the Paris-Laudran University of Salzburg in Austria. In this talk, I present an improved algorithm for so-called exact K-means clustering. That is, an algorithm that produces exactly the same results as a naive implementation, but is much faster. Let's begin with a quick overview. I start with a brief review of standard K-means clustering. Even though everyone certainly knows this very basic algorithm, it can hardly do any harm to provide a quick reminder, which also serves the purpose to introduce some notation. Despite its simplicity, K-means clustering has a few issues, namely that a good initialization is crucial and that the number of distance computations of a naive implementation can be an obstacle for applying it to truly large datasets. Hence, improved algorithms have been suggested. Here I focus on exact ones, that is, algorithms that yield the same results as a naive implementation, but in less time. These algorithms rely on distance bounds that are updated with the help of the triangle inequality. After introducing some principles, I review the basic bounds-based exact K-means algorithms by Elkan and by Hammerly, before moving on to more sophisticated algorithms, like the yin-yang algorithm by Ding et al., which is a hybrid of the two basic methods. In the next step, I discuss the annular algorithm by Drake, which limits the number of centers that have to be inspected to those in a certain hyperannulus, and the exp-onion algorithm by Newling and Fleuret, which limits them to those in a certain hyperball. Based on this foundation, I present my improvement of the exp-onion algorithm, the shallot algorithm, as I call it. Like a shallot is a smaller type of onion, it shrinks the hyperball to be searched. Having presented all relevant algorithms, I turn to experiments in order to assess their merits and to obtain a map that shows for which parameter combinations which algorithm is preferable. Finally, I close the talk with a brief summary. I apologize for telling something which everyone is politely but inexactly supposed to know with a brief review of standard K-means clustering. However, a quick reminder cannot do any harm, and it allows me to introduce, in passing, some notation. In K-means clustering, we are given two things. First, a dataset consisting of n data points in an m-dimensional space, usually r to the mth. And secondly, a number k of clusters that are to be found in this dataset. Each cluster is represented by a cluster center, which is itself a point in the metric space, though not necessarily part of the given dataset. The clustering starts by choosing an initial set of k-centers. A simple and straightforward way of selecting these is to sample uniformly at random from the given data points. This is not a particularly clever way of choosing initial centers, but suffices for now. After initial centers have been chosen, two update steps are executed alternatingly. First, a data point assignment step, in which each data point is assigned to the center that is closest to it, and secondly, a center update step, in which new centers are computed as the vector means of the assigned data points. These steps are repeated until the centers do not change anymore. More formally, let nu m of x denote the center that is the mth closest to the data point x. Then the update steps can be combined and written as this formula for computing new centers. Here, t denotes the update or time step. And the outlier 1 is an indicator function that yields 1 if its argument is true and 0 otherwise. In this formula, nu 1t of xj, which refers to the center that is closest to the data point xj in step t, represents the assignment step, while the fraction as a whole represents the mean computation of the data points assigned to cluster I. It can be shown that this update scheme must converge. That is, a situation in which the centers do not change anymore must be reached after a finite number of update steps. Standard k-means clustering suffers from a number of issues. The first and most obvious one is the initialization, that is, the choice of the initial centers. The problem is that the result quality can depend heavily on the chosen initial centers. A poor choice, and sampling uniformly at random from the data points usually yields a poor choice, can lead to inferior results due to getting stuck in a local optimum. However, there are solutions to this problem. Among the most popular is the Maximin method, which chooses the first center uniformly at random from the data points and all subsequent centers in such a way that they maximize the minimum distance to any already chosen center. An alternative is the k-means ++ method, which also chooses the first center uniformly at random from the data points, but then samples from a distribution that is proportional to the squared minimum distances to the already chosen centers. The latter is the de facto standard for k-means initialization. A second drawback is the number of distance computations. A naive implementation of k-means clustering computes the distances from all data points to all centers and thus requires O of n times k distance computations in each update step. Depending on the number of data points and the number of clusters, this can render k-means clustering unpleasantly slow for large datasets. Essentially, this problem can be handled in two ways. The first is to use approximation schemes for the distances. However, this has the drawback that the results may differ from those of a naive implementation. I neglect this approach here. The second consists in trying to save distance computations by using distance bounds that are updated with the help of the triangle inequality. This talk follows the second approach and extends a known algorithm to reduce the number of distance computations even more and thus to make it even faster. How can distance bounds and the triangle inequality help to save distance computations? The crucial insight is that in order to be able to assign data points to the centers closest to them, it is not essential to know all actual distances. All one really needs to know is which center is closest, and this can sometimes be determined without computing all distances. Sometimes no distances need to be computed at all, sometimes only the distances to a cleverly selected subset of the centers need to be computed. Bounds-based exact k-means clustering algorithms maintain, for each data point, upper and lower bounds on its distance to different centers. These bounds are updated with the help of the triangle inequality applied to the distances the centers moved due to an update. With proper update schemes, these bounds can enable us to ascertain that the center that was closest to a given data point before the most recent update is still closest after the update. Of course, now and then, a computation of actual distances between data points and centers will become necessary. However, by computing some additional information, especially center-to-center distances, tightening the distance bounds can sometimes be done by looking only at a specific subset of the centers. In each update step, it is recorded how far each center moved. In order to distinguish the position before and after the update, a star is added. Note that we cannot simply switch to Cji t plus 1 because the index I does not refer to a specific center here, but to the one that is ith closest to the data point xj, and it may be that the update changes this order. In particular, the closest center before the update may no longer be the closest after the update. Note also that determining how far each center moved requires k additional distance computations, which, however, are outweighed by the distance computations between data points and centers that can be saved. If we know how far each center moved, the triangle inequality allows us to derive how close or how far away an updated center can be from a data point in the worst possible case, provided we know how close or how far away it was before the update. This is where the distance bounds come in. Let ujt be an upper bound on the distance of data point xj to its closest center. Furthermore, let ljit be k-1 lower bounds on the distances to all other non-closest centers. Knowing how far centers moved due to an update, we can derive new values for these bounds. If we look at the upper bound to the closest center, we see from this diagram that it can increase at most by the distance that the closest center moved. Likewise, a lower bound on the distance to a center cannot decrease by more than the center moved. Note that a new upper bound resulting from such an update is tight if the old upper bound was tight and the closest center moved straight away from the data point. Likewise, a new lower bound resulting from such an update is tight if the old bound was tight and the non-closest center moved straight towards the data point. Now for the central question. How can these bounds help to avoid distance computations? Very simply, if the updated upper bound on the distance to the closest center is less than the minimum of the updated lower bounds on the distances to the non-closest centers, the center that was closest before the update must still be closest after the update. We know this because even the worst possible case, that is, the closest center moves straight away from and the non-closest centers move straight towards the data point, cannot have brought any non-closest center closer than the previously closest center. Hence we can assign the data point without computing any distances between this data point and any center. The approach just described, which was developed by Elkan, obviously uses k distance bounds. An upper bound on the distance to the closest center and k-1 lower bounds on the distances to the non-closest centers. It is clearly effective as it provides, by taking the minimum of the lower bounds, the best lower bound for the distance to any of the non-closest centers. However, it has the disadvantage that k distance bounds have to be stored and updated for each data point. Thus, one saves on distance computations, but at the price of a possibly substantial number of bounds updates, depending on the number k of clusters. A straightforward improvement consists in combining all lower bounds on the distances to non-closest centers into a single lower bound LJT. This clearly reduces the update costs. Only 2 bounds have to be stored and updated per data point. However, the second bound has to be updated by the maximum of the distances any of the non-closest centers moved. Hence, the reduced costs come at the price of a lower bound that is likely worse than with k-1 lower bounds. However, in practice, this approach often outperforms the approach based on k distance bounds. A more sophisticated approach, the yin-yang algorithm, is a hybrid of these two extreme approaches. It allows for multiple lower bounds to non-closest centers, each of which refers to a specific subset of the centers. This increases the number of lower bounds, but thus also improves their quality. Each needs to be updated only by the maximum a center in the respective group moved, not by the overall maximum. The center subsets are determined by clustering the initial set of centers using k/10 centers, so that each group contains 10 centers on average and only k/10 distance bounds are needed. Of course, the bounds tests do not always succeed. There will be situations in which they fail, that is, in which the upper bound on the distance to the closest center is not smaller than the minimum of the lower bounds on the distances to the non-closest centers, or the one lower bound on the distance to any of these non-closest centers. What then? Do we have to recompute all distances? Fortunately, we may be able to stave off this costly computation a bit longer. We only recompute the distance to the formerly closest center in order to tighten the upper bound on the distance to it. With this tightened bound, but untightened lower bounds on the distances to non-closest centers, we repeat the test. If the test succeeds with a tightened upper bound, the closest center before the update is still the closest center after the update. Only if the test fails with a tightened upper bound as well, the distances to all remaining centers have to be recomputed. However, there is one more improvement. If we know center-to-center distances, or more specifically, if we know for each center which other center is closest to it, we may be able to infer even more often that the closest center did not change due to the update. Note, however, that this requires computing all pairwise distances between centers. If the distance between the center closest to the data point before the update and another center that is closest to this center exceeds twice the updated upper bound, there cannot be any center closer to the data point than the one that was closest before the update. This is illustrated in this diagram, which shows the worst possible case, namely when the data point and the two centers lie on a straight line. Even in this case, the center closest before the update is still the closest after the update. Unfortunately, even with these tricks, we will not be able to stave off distance computations forever. Eventually, we have to compute distances between a given data point and the centers to determine which is closest. If we use k-distance bounds, then we actually have to compute distances to all centers. There is no way around that because we have to tighten all lower bounds. With the yin-yang algorithm, we may fare somewhat better. The bounds tests may fail only for certain subsets of the centers. Then a recomputation is needed only for those subsets for which the tests fail, while for all other subsets the old bounds can be maintained, at least for now. We are in an even better position if we use only two distance bounds, an upper bound on the distance to the closest center and a lower bound on the distance to any non-closest center. If the bounds tests fail, we only need to find the two closest centers in order to reinitialize the bounds. The annular algorithm exploits this. It uses only two distance bounds, so if the bounds tests fail, the two closest centers are recomputed. The closest center yields the new value of the upper bound uj, the second closest center yields the new value of the lower bound lj. The annular algorithm computes distances only to centers in a hyperannulus around the origin. For this, the distances of the centers to the origin, as well as center-to-center distances, are needed, or more specifically, knowledge which other center is closest to each center. This diagram illustrates the idea. We know that there is a center at a distance uj from the data point xj, namely the previously closest center. Hence we know that the center closest to xj must be in the dark gray circle. If there is no other, it is this one. We also know that there is another center at a distance delta j from the previously closest center. Therefore we know that even in the worst possible case, which is depicted in this diagram, the data point and the two centers lie on a straight line, the two closest center must lie inside the medium gray circle. If there are no others, they are these two. Of course, we cannot search just this circle, because it is centered at the data point. We can only determine which centers lie in this circle by computing distances between all centers and the data point, which is exactly what we want to avoid. Hence we have to search a somewhat larger region, namely a hyperannulus around the origin that contains the medium gray circle, thus ensuring that we will find the two closest centers, since we know that they must lie in this circle. The annulus contains this circle if we choose it in such a way that it has the previously closest center in the middle, and a thickness that is computed from the tightened upper bound, and the distance between the previously closest center and another center closest to it, as shown in light gray in this diagram. Note that, of course, the red line and the green line need not be perpendicular as in this sketch. This was chosen merely for drawing convenience. The exp-onion algorithm is based on the same considerations as the annular algorithm. We have only two distance bounds, so if the bounds tests fail, we have to recompute the two closest centers. The closest center yields the new value of the upper bound uj, the second closest center yields the new value of the lower bound lj. The difference between the two algorithms consists in the shape of the region that is searched for the two closest centers. Instead of a hyperannulus, exp-onion searches a hyperball. This diagram illustrates the idea. With the same arguments as used for the annular algorithm, we know that the center closest to the data point xj must lie in the dark gray circle, and that the two centers closest to this data point must lie in the medium gray circle. Again, we cannot search this circle directly. Rather, we search a larger circle, shown in light gray in this diagram, which is determined solely by center-to-center distances. It is centered at the center previously closest to the data point xj and has a radius that is computed from the tightened upper bound uj and delta j, the distance between this center and another center closest to it. Clearly, this light gray circle contains the medium gray circle, of which we know that it must contain the two closest centers. The Shallot algorithm, which is the main contribution of this talk, is an improvement of the exp-onion algorithm. Hence, it also uses two distance bounds, and it also restricts the search for the two closest centers to a hyperbole. It improves on exp-onion in two ways. In the first place, it maintains not only information about the center closest to a data point, which, in addition to the bounds, is also maintained in the exp-onion algorithm, but also information about the second closest center. This comes at practically no cost, because a recomputation of the bounds requires finding the second closest center. It is merely the index of the center that has to be stored in addition. The advantage of maintaining knowledge of which center was second closest in a recomputation of the distance bounds is that it is likely that if the previously closest center is no longer the closest, the previously second closest center is now closest. Hence, the distance to the second center is computed after the upper bound to the previously closest center has been made tight, but before any other center is considered. If it turns out to be closer to the data point than the previously closest center, it is rather chosen as the center of the dark gray hyperbole, which clearly also leads to a smaller radius. The second improvement results from the insight that whenever the search encounters a center that is closer than the centers currently assumed to be the two closest, the radius of the hyperbole can be shrunk, thus potentially reducing the number of centers that have to be considered. Let me illustrate this possibility. This diagram shows the situation when a better closest center is discovered. This allows us to reduce the upper bound uj on the distance to the closest center, which partially determines the radii of the gray circles. Note that the dark gray circle in the diagram for the exp-onion algorithm has become the medium gray circle, thus effectively getting rid of the distance between the center of the light gray circle and another center closest to it. As a consequence, all circles can be shrunk. As this diagram illustrates, the radius can be reduced even farther if yet another center turns out to be closer. Again, the radii of the gray circles can be shrunk. Note, however, that the centers of these circles do not change. The dark and medium gray circles are always centered at the data point xj, and the light gray circle is always centered at the center that was chosen initially, that is, either the center that was previously closest or the center that was previously second closest, whichever is closer to the data point. In order to evaluate the relative performance of the different algorithms, I created a large number of artificial datasets. Although this may be criticized on the grounds that the results have limited validity with respect to real-world data, it allows for systematically varying parameters and using numbers k that coincide with the true numbers of clusters in the data. Since a mismatch can significantly impact the runtimes, and true numbers of clusters are rarely known for real-world datasets, artificial data appeared to be the best choice. All datasets are comprised of clusters sampled from Gaussian distributions of varying size. The size of the datasets was fixed at 100,000 data points, which seemed to be a good compromise between a sufficiently large size to reliably measure differences and a small enough size to execute sufficiently many runs in order to gain statistical support. I varied the dimensionality m between 2 and 50 and the number k of clusters between 20 and 300. For each parameter combination, I generated 10 datasets, each of which was processed 10 times with different initializations. Initial centers were chosen with k-means ++. As a result, I obtained this map, which shows for each combination of number of dimensions on the horizontal axis and number of clusters on the vertical axis which algorithm performed best. Three things are noteworthy. In the first place, neither of the two basic algorithms by Alkan or Hammerly could compete with the more sophisticated algorithms, as they do not show up on this map. Only the Shallot algorithm, which was developed in this work, the exp-onion algorithm, on which it improves, and the yin-yang algorithm are able to win parameter combinations. Secondly, there appear to be fairly clearly delineated regions of algorithm superiority. Yin-yang wins reliably once the number of dimensions is 20 or higher and the number of clusters is 200 or higher. Thirdly, for low dimensionality or few clusters, there is no clear decision between the Shallot and the exp-onion algorithm. This is strange, since there is hardly any obvious reason why exp-onion should be able to outperform Shallot, especially in such an irregular manner. To compare Shallot and exp-onion directly, I prepared maps that show the ratio of the number of distance computations and the ratio of execution times. These maps are color-coded. Blue means Shallot is better, red means exp-onion is better. This first map depicts the ratio of the number of distance computations. It shows a clear and expected superiority of Shallot. There is no case in which exp-onion needs fewer distance computations, but a large region where Shallot needs only about half as many distance computations. However, this does not translate perfectly into a superiority in terms of execution times. In the region in which its number of distance computations is significantly smaller, Shallot also wins by execution time, and often by a substantial factor. However, the map has a strangely speckled look for lower dimensionality and fewer clusters. A possible explanation of this phenomenon is that the execution times vary more, at least in relative terms, for lower dimensionality and fewer clusters, for which execution times are often very low. This effect may be amplified by the fact that I conducted the experiments with heavy parallelization in order to minimize the total time needed for running the experiments. These maps show that indeed for lower dimensionality and fewer clusters, the execution times vary more, which is depicted here by color coding the ratio of standard deviation to mean. These variations may well explain the speckled look of the earlier maps. Since yin-yang wins for higher dimensionality and many clusters, I also compared yin-yang and shallot directly. Again, the maps are color-coded. Blue means shallot is better, red means yin-yang is better. This first map depicts the ratio of the number of distance computations. It shows a clear superiority of shallot up to about 10 dimensions and about 100 clusters. Beyond that, yin-yang takes over. However, due to the higher costs of updating a larger number of distance bounds, as it is incurred by yin-yang, the superiority of yin-yang for higher dimensionality and many clusters diminishes in terms of execution times. Hence, shallot can extend its region of superiority to about 15 to 20 dimensions and about 160 to 180 clusters. Only beyond that, yin-yang also wins on execution time. Let me summarize. A naive implementation of the k-means algorithm requires O of n times k distance computations in each update step, rendering it slow for large datasets. Improved exact algorithms, that is, algorithms that guarantee the same results as a naive implementation, rely on distance bounds that are updated with the help of the triangle inequality. Bounds-based exact algorithms differ mainly in three elements: the number of employed distance bounds, which may be 2, that is, one upper bound for the closest and one lower bound for all non-closest centers, or k, that is, one upper bound for the closest and k minus one lower bounds for the non-closest centers, or gamma plus 1, that is, one upper bound for the closest and gamma lower bounds, one for each center subset as employed by the yin-yang algorithm. Secondly, whether center-to-center distances are exploited in order to stave off a recomputation of distances between data points and centers. And thirdly, the shape and location of the region that is searched for the two closest centers. Of course, this last distinction applies only to algorithms that use only 2 distance bounds. The proposed shallot algorithm improves over the exp-onion algorithm. It also searches a hyperbole around the previously closest center for the two currently closest centers. However, it may choose a better center for this hyperbole by maintaining knowledge of which center was the second closest in the previous recomputation, and it may shrink the hyperbole radius while searching for the two closest centers. The experimental results demonstrate that the shallot algorithm is superior to other algorithms for a large number of parameter combinations, where the few losses to the exp-onion algorithm are likely caused by technical issues leading to excessive runtime variations for lower dimensionality and fewer clusters. Only for higher dimensions and many clusters, the yin-yang algorithm performs better than the shallot algorithm. Thank you very much for your attention.